Hello guys, my name is IBM and I'm still taking you through magnetic fields and electromagnetic induction. I think this is going to be part 29 of the past paper questions. This is question 88. An electron is traveling in a vacuum at a speed of 3.4 times 10 to the power of 7 meters per second. The electron enters a region of uniform magnetic field of flux density 3.2 milliteslas as illustrated here. The initial direction of the electron is at an angle of 30 degrees to the direction of the magnetic field. When the electron enters the magnetic field, the component of velocity Vn normal to the direction of the magnetic field causes the electron to begin to follow a circular path. So we need to find the component of the velocity. So I will resolve this perpendicular. So this is going to be using 30 degrees. This will be V cos, means sine of 30 degrees. The component there is going to be V sine of 30 degrees. So calculate Vn. So the component of the velocity, the vertical Vn, is going to be V sine of 30, which is 3.4 times 10 to the power of 7 sine of 30. Of course, sine of 30 is a half, so this is going to be 1.7 times 10 to the power of 7 meters per second. So this is 1.7 times 10 to the power of 7. Then the radius of the circular path. Of course, now the magnetic force provides the centripetal force. So magnetic force provides centripetal force. So this means BQV is going to be mv squared over r. And r is going to be equal to mv divided by bq, which is going to be the mass of the electron, that is 9.11 times 10 to the power of minus 31 kilograms. The speed, remember the vertical component, the perpendicular to the magnetic field, is what provides the centripetal force. So this is going to be 1.7 times 10 to the power of 7. That is, we need the component of the velocity perpendicular to the magnetic field. Then divide by B. B was 3.2 milliteslas. So this is 3.2 times 10 to the power of minus 3. Then times Q, which is 1.6 times 10 to the power of minus 19. So 9.11 exponent minus 31. Then times 1.7 exponent 7. Divide by 3.2 exponent minus 3. Divide by a 1.6 exponent minus 19. So that is 0.030. State the magnitude of the force, if any, on the electron in the magnetic field due to the component of its velocity along the direction of the field. So parallel to the direction of the field, the component parallel to the direction of the field has no causes no force, because whenever the force is parallel to the whenever the particle moves parallel to the magnetic field, the magnetic force is zero. So the component parallel to the field will cause zero force, because the magnetic force only acts on a moving particle if its velocity has a component perpendicular to the field. The magnetic force only acts on a moving particle if its velocity has a component perpendicular to the magnetic field, which means the component parallel to the magnetic field causes no force. Use the figure, use the information from A and B to describe the resultant path of the electron in the magnetic field. So because the magnetic force, the magnitude of the force caused by the horizontal component is zero, yet there is a force caused by the vertical component. That means the particle is going to follow a circular path which is going to be stretched out in the horizontal plane, resulting into a helix. So the path is a helix. The path is a helix, or you can call it a coil. It's like a stretched out spring. So the component of the velocity normal to the field gives rise to circular motion because it provides centripetal force. However, there is also a component of velocity along the direction of the field. So consequently, the electron executes a circular motion and it moves in a direction normal to the plane of the circle, or normal to the plane of the circular path. Therefore, the circle is going to be pulled out into a helix, rather like coils of springs which have been stretched out. So the path of the particle is going to be like this, like a stretched out coil of a spring, just like that. So the circular part is because of the vertical component of the velocity, and then the stretching out of this is due to the horizontal component of the velocity. A solenoid is connected in series with a battery and a switch, as illustrated in the figure here. Okay. A small coil connected to a sensitive ammeter is situated near one end of the solenoid. As the current in the solenoid is switched on, there is a changing magnetic field inside the solenoid. State what is meant by a magnetic field. So we said a magnetic field is a region of space where a force is experienced or exerted on a magnetic pole or a moving charge or a current carrying wire or current carrying conductor, or it is a region of space where a force is experienced by, a region of a space where a current carrying conductor, a moving charge, or a magnetic pole, or a magnetic material experiences a force. On the figure, draw an arrow on the axis of the solenoid to show the direction of the magnetic field inside the solenoid. Label this arrow P. So we just use the right hand grip rule as illustrated by this image here. Imagine gripping your coil in your right hand with the thumb pointing in the direction of the north and the fingers folding in the direction of the current. So if you grip the coil in your right hand, you notice that the fingers are folding in this direction here. So that where the thumb points is the north end. So this is going to be the north, the other end is going to be south. And the field lines originate from north and terminate to the south. So here they are terminating and here it is originating. So the arrow is going to be like this. And they said label this P. So I'll draw a line along the axis. Let me use a ruler. So draw a line along the axis. Label this P. As the current in the solenoid is switched on, there is a current induced in the small coil. This induced current gives rise to a magnetic field in the small coil. State Lenz's law. Of course, we have already stated Lenz's law, but I need to restate it because I'm going to be referring to it to answer other parts of the question. So the direction of the induced EMF The direction of the induced EMF is such as to cause effects that tend to oppose the change producing the direction of the induced EMF is such as to cause effects that tend to oppose the change producing the EMF, or the change to oppose the change producing it. Use Lenz's law to state and explain the direction of the magnetic field due to the induced current in the small coil. On the figure, mark the direction with an arrow inside the small coil. Okay, so the direction of the induced EMF is always such as to oppose the change producing it. So if the magnetic field here is downwards and there's an induced EMF in this coil, the induced EMF is going to be such as to oppose the change which is producing it. Therefore, this side is going to be north. If this is north, this side will be north and this will be south. No, that is not true. So the direction of the induced EMF is going to be such as to oppose the change producing it. We said, remember, this is north and this is south for this coil. That means this side of the coil is going to be south to oppose this south, and this will be north. Therefore, the magnetic field is going to be in the small coil is going to be upwards. So I'll line here, and the arrow is going to point in that direction, because the direction of the induced EMF is always such as to oppose the change which is producing it. So the question was, use Lenz's law to state and explain the direction of the magnetic field due to the induced current in the small coil. On figure 8.1, mark this direction with an arrow inside the small coil. So I've already added the arrow at the center of the coil. So the magnetic field in the solenoid is increasing. The magnetic field in the solenoid is increasing. How do we see that is increasing? That is when we close the switch, the magnetic field in the solenoid increases. So because it's increasing, by Lenz's law, the field due to the induced current in the small coil must be, of course, by Faraday's law, an EMF is induced in the second coil. But by Lenz's law, the field due to the induced current in the small coil must be in the opposite direction to oppose the increase. When you close the switch, the magnetic field in the coil increases from 0 to some value. So the induced EMF in the small coil must be such as to oppose the change producing it, which means that the field to the induced EMF or induced current in the small coil must be such as to oppose the direction or to oppose the increase. Therefore, it must be in the opposite direction to oppose the increase. And therefore, the arrow should be in the opposite direction to that. So the current which flows here when you close the switch must be such as to oppose the increase in the magnetic field around the solenoid. Therefore, the arrow should be in the opposite direction to that in the solenoid. A small coil has an area of cross-section 7.0 times 10 to the power of minus 4 meters squared and contains 75 tons of wire. A constant current in the solenoid produces a uniform magnetic flux of flux density 1.4 milliteslas throughout the small coil. The direction of the current in the solenoid is reversed. Current is reversed in a time of 0.12 seconds. That means time from 0 to maximum is 0.12 divided by 2 seconds. Calculate the average EMF induced in the small coil. So we know that EMF is directly proportional to the rate of change of magnetic flux linkage. So EMF is going to be N times change in flux over time. Or it can be N, B, A over T. The number of turns is 75. The magnetic field is 1.4 times 10 to the power of minus 3. The area of cross-section is 7.0 times 10 to the power of minus 4. Then the time is 0.12 divided by 2 because it is reversed. So from our calculator, I'll just say 75 times 1.4 exponent minus 3 times 7 exponent minus 4 times 2 divided by 0.12. So that is 1.225 times 10 to the power of minus 3, or approximately 1.2 times 10 to the power of minus 3. So this is 1.2 times 10 to the power of minus 3. The particle has mass m, charge positive q, and speed v. The particle enters a uniform magnetic field of flux density B such that on entry it is moving normal to the magnetic field as shown in the figure. Okay, so on entry it is moving perpendicular to the magnetic field. The direction of the magnetic field is perpendicular to and into the plane of the paper. On the figure 8.1, draw the path of the particle through and beyond the region of the magnetic field. So we just use Fleming's left-hand rule. Because the particle is entering perpendicular to the magnetic field, it experiences a force whose direction is given by Fleming's left-hand rule. So since the magnetic field is into the page, the first finger should point into your paper. The second finger, because the particle is positive, the second finger points in the same direction as the motion of the particle. And when you do that with your left hand, the thumb points upwards, which means that the force at entry is upwards. So the particle is going to be deflected. Because the magnetic force provides centripetal force, the particle is going to move at an arc, an arc of a circle upwards. Of course, when it emerges from the field, you use a ruler to draw a tangent to the curve. So the path is going to be upwards because the magnetic force is upwards. There is a force acting on the particle, causing it to accelerate. Explain why the speed of the particle on leaving the magnetic field is v. On entering the magnetic field is v, and on leaving is v. Note that the magnetic force is perpendicular to the direction of motion of the particle, and therefore it will not always change the speed. So the magnetic force is always perpendicular. The magnetic force is always perpendicular. Is always perpendicular to the direction of motion or to the velocity, or it's always perpendicular to the direction of the speed. Thus, the force cannot change the speed, but cause centripetal acceleration. So the force cannot change the magnitude of the speed, can only cause centripetal acceleration. The particle in B loses an electron so that its charge becomes positive 2q. So charge becomes positive 2q. Its change in mass is negligible. Determine in terms of V the initial speed of the particle such that the path through the magnetic field is unchanged. Explain your working. So we have already mentioned that the magnetic force provides the centripetal force. Therefore, B QV is equal to mv squared over r. So initial speed, I'll call this initial speed V, was equal to B Q R over m. That is before changing the charge. So the new speed is going to be equal to, using the same similar formula, is going to be B, where there is charge, I'll put there twice Q, and R, because they said in terms of V, the initial speed of the particle such that its path through the magnetic field is unchanged, so the radius of the path is the same, and they say the mass was negligible, so this is over m. So when you simplify this one is the same as twice B Q R over m, which is actually twice V. So the speed of the particle should be twice V, if V is the initial speed. A solenoid is wound on a soft iron core as shown in the figure. A coil C having 120 turns of wire is wound onto one end of the core. The area of cross-section is 1.5 centimeters squared. A hole probe is close to the other end of the core. When there is a constant current in solenoid S, the flux density in the core is 0.19 teslas. The reading on the voltmeter connected to the hole probe is 0.20 volts. The current in solenoid S is now reversed. Current is reversed in a time of 0.13 seconds, which means current takes a time of 0.13 divided by 2 to change from maximum to 0. Just from maximum to 0, not from maximum to maximum. Calculate the reading on the voltmeter connected to coil C during the time that the current is changing. So in other words, we want the induced EMF. The induced EMF is directly proportional to the rate of change of magnetic flux linkage, which is N times change in phi divided by time, or which can be N BA divided by time, which will be the number of turns is 120 times B, which is 0.19 teslas, times the area, which is 1.5. We have to change it to meters squared, that is times 10 to the power of minus 4, divided by the time, which is 0.13 divided by 2. So I'll just press my calculator, that is 120 times 0.19 times 1.5 exponent minus 4 times 2 divided by 0.13. So that is 0.053. 0.053 volts. Complete figure 9.2 for the voltmeter readings for the times before during and after the direction of the current is reversed. After the direction of the current is reversed. Okay, so we want to complete a table for the voltmeter reading for the times before, during, and after. So the voltmeter connected to the coil C. The voltmeter connected to coil C indicates the value of the induced EMF. Remember, the induced EMF is directly proportional to the rate of change of magnetic flux linkage, which is also proportional to the rate of change of the current in coil S. So the induced EMF here is also directly proportional to the rate at which current in coil, not in coil, in the solenoid S, current in solenoid S changes. So the voltmeter connected to the Hall probe here at the bottom indicates the Hall voltage, and since we know that VH is equal to BI over NTQ, so it means VH is directly proportional to the current I. So before current changes, it means it's constant. So the rate of change is 0, which means the induced EMF is going to be 0 in coil C. When the current is constant, the induced EMF in coil C is 0, but the Hall voltage is going to be maximum and constant. So let's say before it changes, the reading of voltmeter connected to coil C is going to be 0 because there is no change in the current. The induced EMF, the Hall voltage depends on current. So this one depends on the rate of change. And this one, Hall voltage is directly proportional to the current. So when the current does not change, the induced EMF is 0. When the current is constant, the Hall voltage is 0.2. Then during current change, when current is 0. So when there is current change, when current is 0, of course, the Hall voltage reading is going to be 0 because it depends on the current. But during current change, when the current is 0, it means it has changed from maximum to 0. So the induced EMF is going to become a certain value. So during current change, the induced EMF is, we have said that during the current change, in a time of 0.13 seconds, the reading of the voltmeter in coil C is 0.05. So during current change, the induced EMF or the reading of the voltmeter is going to be 0.053. Then after current change, again the current becomes constant. Remember, when the current becomes constant, the rate of change of current is 0. That means the magnetic flux linkage is constant. The induced EMF here is going to be 0. But after current change, now the current again becomes constant. But here it was before current changes and after current changes. Therefore, it is going to change the sign. So after current changes, it has reversed direction. It means we started from a positive current to a negative current. So it starts from positive to negative. After current change, the current has changed direction or has reversed direction. It means it's again constant. So the rate of change is again 0, which means the induced EMF is 0. But since the current has now reversed direction, it means VH also changes its polarity. Therefore, this is going to be minus 0.20. Okay, that is the explanation there. A stiff copper wire is balanced horizontal on a pivot as shown in the figure here. Okay. Section P, Q, QR, and RS of the wire are situated in a uniform magnetic field of flux density B, produced between the poles of a permanent magnet. The perpendicular distance of PQRS from the pivot is 7.5. So the perpendicular distance there is 7.5. When a current of 2.7 amperes is passed through the wire, A small mass of 45 milligrams is placed at distance 8.8 centimeters from the pivot in order to restore the balance of the wire as shown in the figure. So in other words, we must attach a small mass in order to restore balance. Initially, we didn't need that mass. Okay. Explain why when the current is switched on, the current in the sections P, Q, and RS of the wire does not affect the balance. So section PQ, assuming that this is north, I'm going to assume this is north, this is south, which means the magnetic field is in that direction. If you try to make the first finger in that direction, the current is flowing like this, like this, like this. So the second finger upwards, it means that the field, the force on this section is going to be into the page or in that direction. And then if you try the same on this section, RS, the current is flowing downwards, so the first finger is downwards. The field is in this direction, so second finger is in that direction. It's not very perfect here, but the thumb is going to be out of the page, or in this orientation, it would actually be in this direction here. So that means I was supposed to twist this, but I couldn't twist that. It would have been in this direction here. Or if I'm to use the correct orientation, making this south, this would be in this direction here. Field in that direction, actually field wouldn't be like that perfectly, field would be like this. But I couldn't twist this hand in that direction. The current is downwards, field like that. It means the force will be in this direction, just opposite to the other one. So therefore, the forces are going to be acting in the same line, but in opposite directions. So they are going to cancel out each other. Therefore, they have no effect onto. They have no effect onto. They have no effect on the balance of the wire. Therefore, we shall simply say that the forces on PQ and RS are horizontal, and so they cause no moment. First of all, they are horizontal. One is in this direction, one is the other direction, the horizontal plane, so they cause no moment. Or you would think about it like this, that the forces on PQ and RS are equal, but in opposite directions. And so there is no net force. There is no net force. There is no net force. Or let me say they cancel out each other. And so they cancel out each other. The length of section QR of the wire is 1.2 centimeters. Calculate the magnetic flux density. So, of course, we know that the force on QR is going to be equal to B. And remember, to restore balance, there was a change in clockwise. Of course, the force is going to cause an anti-clockwise moment. Therefore, we have to add a mass to cause a change in a clockwise moment, and these two changes must be equal. So the force on QR, we said it is equal to B. And to restore balance, the change in clockwise moment should be equal to the change in the anti-clockwise moment. So taking moments about the pivot here, the weight we have added here is going to cause clockwise moment, yet the force on QR is causing anti-clockwise moment. So this means we are going to say that Bill, that is the force, times perpendicular distance, I'll call it X, should be called the change in moment the other side, because we have added the weight, so that is going to be mg times the perpendicular distance, let me call it y. So we have B times the current, which is, the current is 2.7. The length of the section in the section QR is 1.2 centimeters, which is 0.012 meters. That is the force. Perpendicular distance from the pivot was 7.5, which is going to be 0.075. This should be equal to the weight. We added 45 milligrams, that is 45 times 10 to the power of, is it milligrams? Yes. Power minus 3 grams, then times 10 to the power of minus 3 to change it to kilograms. So that is 45 times 10 to the power of minus 3 to change it to grams, times 10 to the power of minus 3 to change it to kilograms, then times 9.81 times the perpendicular distance. So the perpendicular distance is 8.8 centimeters, which is 0.088. Okay, I'll just press the calculator. 45 exponent minus 6 times 9.81 times 0.088 divide by 0.075 divide by 0.012 divide by 2.7. So that is 0.016. So B is going to be 0.016 Teslas. Okay, I think part 29 should stop there. See you in part 30.